Bismillahirrahmanirrahim. Assalamu alaikum. In the last couple of modules, we have been talking about the K nearest neighbor algorithm. In today's video, we'll focus on the concept so-called the curse of dimensionality. You hear this term very often in the machine learning literature or in the research papers related to machine learning area. I will give you a quick overview of the concept of the curse of dimensionality, and I will try to explain with the help of a couple of illustrations. Okay, let's formally begin. Uh, the curse of dimensionality, it refers to the problems or phenomena associated with classifying, analyzing, or organizing the data in higher dimensional spaces. And these problems do not appear and do not arise in low dimensional settings. For practical applications in machine learning, we deal with spaces of high dimensionality. We handle many input variables. And as we now discuss, these higher dimensional data spaces pose some serious challenges and are an important factors influencing the design of machine learning methods, systems, and techniques. And therefore, we must handle these problems intelligently during the design of machine learning algorithms. If I explain this curse of dimensionality, so the concept is the size of data space is huge when we deal with high dimensional data sets. In other words, we say that the size of the feature space grows exponentially with the number of dimensions of the data sets. And if we want to maintain the same density of points in the high dimensional space, we require the size of the data set must also exponentially grow so that we get the same number of data points per unit volume or per unit area in the higher dimensional space. This concept of the curse of dimensionality is used interchangeably with the term peaking phenomena or Hughes phenomena. Right. So if you hear the curse of dimensionality or peaking phenomena or Hughes phenomena, so these correspond to the same concept that the size of data space is huge when you deal with high dimensional data sets. To illustrate this, let me give you one example. So we take a region of space and we divide this into regular cells for when we have a one-dimensional space real line, or we have a plane and d is equal to 2, or we have d is equal to 3. Right? So I have divided the space into regular cells, and we see that the number of such cells grow exponentially with the dimensionality of the space. Right? If you take d is equal to 4, the number of cells would grow exponentially, and so on and so forth. We need exponentially large amount of training data to ensure that these cells are not empty, or the density of points per cell would remain the same. Right? Okay, let me try to explain this further with the help of another example. We take a ball of radius r, and this is how it is. This is how we define a ball of radius r, right? So B denotes a ball. Hang on. Yeah. So B is a ball of radius r such that it contains all the points in d-dimensional space that has a radius less than or equal, that has Euclidean norm less than or equal to r. Right? This is interior of the ball. So a ball that is filled with all the points. For such a ball, we define its volume given by some constant times radius raised to the power d. Right? If you recall your high school mathematics, how do you define area of a circle? Right? So circle is a disk. In fact, it's a filled circle, it's a disk. So disk, the area of a disk is pi r square. Right? So for a disk, kd is equal to pi r to the power dimension, right? If you have a ball in a three-dimensional space, kd would be given by 4 by 3 pi, and then you get r cube. That's how you define a volume of the ball in three-dimensional space, right? But for any dimensional d, the constant k would depends on d. For example, when d is equal to 2, this kd is equal to pi. And when d is equal to 3, kd would be 4 by 3 pi, and so on and so forth, right? So kd would change with d. And then dependence on radius is given by this term, r to the power d, right? If you want exact definition of this constant kd, so kd is given by this formula. Okay, so we have defined a ball, and we have defined volume of a ball in d-dimensional space. Okay, now I'm going to use this information to take a ratio of the volumes, right? So in fact, so I will take two balls, right? So the one ball with the radius 1 and another ball with the radius 1 minus epsilon, right? And I want to find out that what is a fraction of a volume between the ball of radius 1 and radius 1 minus epsilon. It simply means I want to find, so the volume of this region, I call it shell, right? This is a shell that has the outer radius of 1, inner radius of 1 minus epsilon, right? It's a shell in d-dimensional space. And I want to find the fraction of volume in this shell with respect to the volume of a unit ball, right, which is the outer ball. Okay, we can, so if this is the volume definition of volume, we can define such a ratio as a volume of a ball with unit radius minus volume of the ball with 1 minus epsilon radius, and divided by volume of unit radius ball, right? And if you just substitute this definition of volume, so what you get is this: the constant kd would appear in the numerator and also in the denominator, so that will be cancelled. So you get 1 minus epsilon raised to the power d, right? So this is the volume of this shell normalized by volume of ball of radius 1. Okay, I think this all makes sense, right? Okay, let's plot this, right? Let's plot this for different values of d. So this fraction depends on d and epsilon, right? So let's plot this for different values of d versus epsilon. So we want to draw the volume of this shell for different values of epsilon and different values of d, right? So if you plot this for different values of d, so this is what you get, right? When d is equal to 1, right, so you get this plot. So as epsilon growing, the fraction of the volume in the shell keeps on growing, right? This makes sense, and this is so intuitive, right? Similarly, when d is equal to 2, right, so you expect the volume of the shell to grow like a square root term, right? So that's how it should be growing, right? What's happening when d is increasing, and d is equal to 10, 50, 474, right? So for very small value of epsilon, right? So let us say when I take epsilon is equal to 0.1, and if I extend this, right? So when d is equal to 50, right? So 99% of the fraction of the volume is the volume of the shell. That means if you what's the difference between the radius? So the radius of outer ball is 1, and the radius of inner ball is, if I take epsilon 0.1, the radius of inner ball is 0.9. But when d is equal to 50, right, the the volume of the shell would be 99% of the total volume, right? That means the volume of the inner wall would be simply 0.01, right? So 99% of the volume would be would be in the shell. Are you getting this? Okay, or we can say most of the volume of a ball is concentrated in a very thin shell near the surface, and this volume keeps on growing as d is growing, right? So let's see if I fix epsilon, and so if I move along this dimension, so this is the d is growing and the volume of fraction is also growing like this along this if I fix epsilon. I hope this all makes sense. Okay, let's use this data and try to interpret it in another way. Right? So I give you another viewpoint to interpret this information. We want to calculate probability that a uniformly distributed point is inside the shell or it is inside the inner ball. Inner ball means this blue ball, and the shell corresponds to this gray area. Right? And say we take epsilon is equal to 0.1, and I compute these numbers for different values of t. Right? Say for d is equal to 1, probability that you randomly distribute a point inside a unit ball, it would lie in the shell area, the probability is 0.1. And the probability that it lies inside this blue ball or inside inner ball, the probability is 0.9. When d is equal to 2, the shell probability, the probability that it lies inside the shell keeps on growing. And as you keep on increasing d, so say for d is equal to 50 and above, it's almost certain that all the points you distribute inside a unit ball, most of them, almost all of them would be placed inside the shell area, in this gray area, right? If we talk about numbers, so you take d is equal to 50 and you distribute 1000 data points uniformly inside a ball of radius 1. Only 5 out of those 1000 data points would be inside the inner ball. All of them would be on the boundary. That means if you take a distance of those points from the origin, the distance of every point is almost 0.9 or is greater than 0.9, right? Because we have taken epsilon is equal to 0.1. Are you getting this? Or we can say these points are almost at the same distance from the origin. In fact, they are very far from each other as well. So they are far from the origin and they are far from each other as well. Right? When I take d is equal to 400, right? So I get a probability that they are inside the inner ball as a very, very small number, right? So x tends to minus 19. Almost all points lie on the surface of the ball. Or we can say, if you take a test point on the origin and you take d is equal to 400, almost every point, you place any point, you pick a point that will be at the same Euclidean distance from the origin. Can I say it like this? If I take a test point on the origin, right, and I have 10,000 points in my training data, and I want to find the nearest neighbor from a test point. Can I find nearest neighbor? I can find neighbors, but all of those neighbors would be almost at the same distance, right? This is we have just illustrated that all of the points would lie at the same, almost at the same distance, right? They always lie on the surface or near the boundary. As d increases, every point is far from other point. So they are far from origin, and they're also far from each other. Okay, I think you are seeing this for the first time, or if you have seen this before, normally I say that our geometrical intuitions, which are formed through a life spent in a space of 3 dimensions, uh, those intuitions can fail badly when we consider spaces of higher dimensionality. Because we try to visualize things in a 3 dimensional space, but those intuitions can fail badly when we deal with higher dimensional spaces. Maybe I can give you these numbers for some other value of epsilon. Let's say I take epsilon is equal to 0.01, and if I compute these numbers, so epsilon equal to 0.01 means very, very thin shell around the surface, right? The radius of the width of the shell is 0.01. Right? And if you see, when d is equal to 784, so again, almost all of the points lie inside the shell in a very, very small region. It appears to be, it appears small region, but it's not small, right? Because the fraction of the volume of the shell relative to the fraction of the whole unit ball is almost 1, right? So you increase by epsilon, right? And that means, but the volume of fraction will be almost, yeah, most of the volume would be inside that very, very thin shell. Okay, let's make a connection of this curse of dimensionality with KNN. Although I have briefly explained the connection in the previous slide, but let's make a formal connection with KNN, and why does, what's the problem with KNN in higher dimensional spaces? What is the impact of this curse of dimensionality on KNN? Okay, with the increase in the number of features or number of dimensions, data points are never near to one another. This is a conclusion of our previous analysis, that we do not have data points near to one another. So every data point is far from another data point. So this curse of dimensionality phenomena makes learning problems very, very complicated, especially when we want to learn a state of a nature from finite number of data samples in high dimensional feature space. Right? This KNN. So in KNN, we carry out predictions about test point, assuming we have data points near to the test point that are similar to the test point. Right? This is what we learned about K-learning algorithms. So K-learning, K nearest neighbor algorithm needs you to trust the assumption that its nearby neighbors are similar to it. This simply means that your success when using the K nearest neighbor algorithm is very dependent on having a dense data set. If you don't have a dense data set, so you expect KNN performance to degrade. Okay, how? At face value, it appears that K nearest neighbors would be especially sensitive to this problem, right? In fact, every machine learning algorithm needs a dense data in order to accurately predict over the entire data space. So, but the question here is, what makes KNN very vulnerable or very sensitive to this curse of dimensionality? Okay, the special case with K nearest neighbor is that it requires a point to be close in every single dimension. We have algorithms, we will talk about algorithms, for example, regressions, to carry out regressions. They need points to be close together along some axis, right? But K nearest neighbor doesn't work that way. K nearest neighbors requires points to be close along every axis in the data space, because it works on the principle of, it works on the computing distances, right? right? If the distance matrix says all the points are at the same distance from your test point, then you cannot have sorry, then you cannot have near neighbors, right? Right? And due to this, we say that KNN is very sensitive and it is vulnerable to the curse of dimensionality. Having said this, we see that KNN still works, and you will see in your programming assignment that KNN still works for in high dimensional spaces as well. But why does KNN work, right? And there are two connected explanations, the working of KNN in higher dimensional spaces. The first explanation is that the data in real world is confined to a region, and effectively the data has lower dimensionality. So all the data lies in a higher dimensional space, but it is confined to a small region of that space, right? And therefore, when you only focus on that region of the space, that region of space has effective lower dimensionality. Example could be if your data lies on along a single line, say in R100, right? So the effective dimension, right, of the data is just one, because most of the data points lie along that line, right? Or if your data points lie in a plane in a say 6-dimensional space, right? So the effective dimensionality of your data would be 2, right? And we will talk about this later in the course. And the second possible explanation is that real world data exhibits smoothness that enables us to make predictions exploiting interpolation techniques, right? So in real world data, we do not have very, very large variations. So in real world data, we expect that it would exhibit some smoothness in a higher dimensional space. And these two explanations, in fact, form basis the working of KNN in higher dimensional spaces. The first one, again, we can connect this to a concept of dimensionality reduction, and we will, as I said in the previous module, we will talk about this concept later in the course. For the second one, I can give you a couple of examples. I have given you the data along a line or a plane in a higher dimensional space, or we want to detect orientation of an image, orientation of an object in an image, right? So say you have a data that is, you take out, say, a 6 megapixel image, right? That means if you talk about the number of pixels, right? So the number of dimensions of the feature space is in millions, right? But you only want to detect orientation of an object, and orientation of an object can be explained with just one dimension, right? For example, you want to recognize face, right? Again, if you take all the pixels of an image, you may have number of features in millions. But we see that, in fact, we do some feature engineering, and we define some features on an image, say 50 or 71 features, and just using 50 or 71 features, we can carry out face recognition, we can carry out emotion recognition, we can detect whether the eyes are closed or open in a face, and so on and so forth. Another example could be spam filter. So it's a simple binary classification problem. Yes, spam, not spam. You get an email, spam, not spam. But if you talk about number of features, right? So number of features in this case is the words in your email, right? The words in the subject. So again, the feature space is huge, right? But we can employ some intelligent techniques to gather those features and we can reduce the number of features so that we only use a subset of the features, or we can use less number of features to carry out this spam filtering detection. Okay, so this was a quick overview of the curse of dimensionality concept and its relation with KNN. We will talk about this concept later in the course, the curse of dimensionality concept. Right? So इसके बारे में हम बार-बार बात करते रहेंगे, and we will see. In fact, there are benefits that are associated with this higher dimensional curse, and most of the times we exploit those benefits, those properties, this separation of the points in the higher dimensional space to carry out machine learning tasks. Okay, so we stop here and we will continue in the next module, inshallah.